Now we will see some adversarial approaches for deep learning, which is kind of important elements. The first point is about adversarial data, something that we figure out in the year 2010s and so, is that, deep neural networks are able to have really good performances, but there are ways to generate, I would say, very small modifications to samples like images, not only images, but it has been demonstrated in part on images. So with really small but really well-defined modifications, kind of really small noise, but not random noise that is guided for some task, that will be able to fool a neural network. In this example here, we have clean images. Here we see it's a meerkat with confidence of 65%. We add this really small noise. It is visible here, but the epsilon is really low, so it's really not that visible. It modifies the image in a way that is likely not perceptible by humans, or really just light, and it's not affecting at all the quality of the image in terms of our perception. And then the neural network will be completely fooled and will say it's a school bus with high confidence. So this is a classical example of things that we observe. And so we have methods that can do that can modify samples to fool a network. And that is the explanations provided on that, is that we are dealing with a distributed representation in a very high dimensionality space. And that means that, in such high dimensionality space that is very difficult to visualize, we could expect that, in some specific directions, we can be really close to a decision frontier. So because we are kind of cutting the space in many, many ways with different hyperplanes, and this is over like really huge dimensions. And if we figure out the right direction, we can just make a really small step and move on the other side of the hyperplane and change completely the decision. And so this is, I would say, coming directly from this like distributed representation approach. So this is a current difficulty. There are not like no magic bullet in terms of solving this. There are some approaches that allow to kind of robustify the neural network, but we need to be cautious. And this gets us to the point that, these models are not necessarily super well understood in the way they are working. And this is an example of something that we didn't expect at first, and that is object of concern by some part of the research community to kind of figure out how to make the networks much more robust to such, I would say, adversarial samples. In fact, there's like, I would say, different what we call attacks. And this kind of first approach, a very simple way to generate this noise over the current data is to make use of methods like the fast gradient sign method. Basically, what it does is computes, I would say, the directions in the X. So it's really taking the derivative of the loss, but not according to the weights of the model. We just have some neural network. We keep that fixed, but we do the derivative over the X, which is the input data, for example, the image. And we try to figure out the direction of the gradient, the modification to the X, the modification to the image. So what is the direction according to the gradient? And we just use the sign. We don't do, I would say, a fine step, but we do a step that is modulated by the sign times some epsilon that can be really small. So we apply a really small modification in the direction of the gradient that seems to be modifying and affecting the loss as much as possible. So this gives us the directions where the decisions of the neural network will be modified the most. And applying this, possibly several iterations of that, it can lead to, I would say, a new X that will be very similar to the original X because the steps will be really small, but at the same time will be fooling the network, will be making, I would say, bad decisions, wrong decisions versus the original X that was correctly classified. So there are several variants. This is the basic one. The FGSM is a basic one. It is relatively still effective. There are some other approaches that are even more effective, possibly more computationally intensive, but that gives the idea of, doing gradient descent in the space of X, not in the space of theta. So we are doing gradient descent in the space of the images or the data, whatever. And this is possible with our software libraries we have with deep learnings to do such a thing. And they are like, over these attacks, we also have defense mechanism. There are several of them. Many have been proposed in the research literature. One that is quite effective still is simply what we call adversarial training. And the idea is to produce, I would say, new samples that are, I would say, made with FGSM. And so we use this sample with FGSM as a way to augment the training set. So we will add more samples to the training set, which are in fact modification of original data we found there, modified with FGSM. And then we will train the network with this extra data set, the extra training, augmented training set from the original plus the modified attacked version of the data to make the network more robust. And it works quite well in practice, exposing the network to many of these samples generated with FGSM will allow the network to kind of reorganize the boundaries and possibly being less fragile versus these kind of samples. There are also other adversarial approaches. The most known one is probably the GANs, the generative adversarial networks. So the idea of GANs is in fact to put into competition two neural networks. So we say we have two neural networks. They are adversarial in the sense that they are in a game. And in that game, we have a discriminative network. The discriminative networks try to differentiate between real data versus generated data. So we are in a context where we have capacity to generate fake data. And we also have access to real data, and our discriminative model tries to differentiate between these two. So it's basically a binary classification model, and it tries to say this is a real data, this is a fake data. And behind it, we have the generative model, which is a network that is used to produce the fake data. And this generative model is in competition with the discriminative model in the sense that, it tries to maximize the error of the discriminative network. So the discriminative network is trying to minimize its error, but the generative network is trying to maximize the error of the discriminative model. So it is kind of fighting with it in order to generate better results. Because if the discriminative model is better at discriminating between real and fake samples, the generative model should learn to produce better fakes that will induce the discriminative model into error. And this is also interesting because there is no need for labels in such approach. We just need a data set of real data. And with this kind of approaches, we will just try to learn a way to generate good fakes that are similar to the original data. An example of that is what we call image-to-image translation with conditional GAN. So it's more than that because we are conditioning the GAN on something. So here, like for example, we say, we have this kind of black and white data. We just put it as a condition to the generative model and the discriminative. We say, this is the black and white, and this is the corresponding color data. And then the generative model tries to produce this color version, but we also give to the discriminative model some real color version of black and white data. And so with it, the GAN will learn to produce color version of the original black and white data. Likewise, we can just move an image from day to night, or we can just move an image from like having this kind of rough, sketchy version of a house facade, a building facade. We go from that to the real image of a facade. So it's possible to have real data where we just take the real image and we just extract this kind of abstract representation. But we want then to get the GAN, the generative network, to be able to produce new images from just this kind of labeled view of a facade. So the GAN work that way. So we have, like I say, a discriminative network and a generative network. So and we have a real data set with real data. And so we just feed the discriminative network with a mix of real and generated data in a random way. And the discriminative network try to figure out, is it real or fake? So this is really and use this into a binary classification, try to works well with that. And the gradient starting from like the loss of the discriminative network, try to minimize this loss for the discriminative network. But for the generative network, we add a minus sign here. We just kind of do the opposite. We try to maximize that loss according to the signal we got through. And the point is that we are back propagating through the discriminative network first and then through the generative network. So we've got this signal that is passing through this here and then through that there. And the generative network is updated according to that. And it allows to get the signal from a binary signal through the data, the generated data, and directly in the generative network. And it has no necessarily real inputs. It can be conditioned like with some thing that we saw before, or we can just put some random noise as input to get it to generate something.